So today is going to be probably a little shorter, and we're going to focus on those two, which are about Laplace transforms. So that's what we're talking about. Now, the nice thing about Laplace transforms is that, in some sense, you don't have to memorize too much. You've got a table. And now this isn't just any table. I was actually able to sneak this. This is the exact table from the final. You're like, that looks kind of like the table from the second exam. It is. So you know the table. Now you might be thinking, am I really doing calculus if I keep looking things up on tables? That doesn't feel very calculus-like. But actually, it is incredibly calculus-like. Because if you think about, like, how do I take derivatives and how do I take integrals? You'll probably say, well, I have a bunch of things memorized and I just recall it. Well, that means that you actually have a table in your head. And that when you say, oh, the derivative of sine is cosine, you went and looked it up. You're so familiar with that table, you don't have to refer to a paper table anymore. And someday, you might get to that point with Laplace transforms. I've heard some engineering topics really like Laplace transforms. And so depending upon what you do, this will become just as natural to you as derivatives and integrals. Okay, so I'm not going to spend too much time on this table. I just want to sort of say, what's our basic idea? So we're going to have these Laplace transform problems. And more or less, there's a flow to them. And it goes along the lines of the following. You're given a problem. Okay, great. And then what you have to do is you have to do some preprocessing. So what do I mean by that? Well, what I mean is you have to take what's given to you and you have to figure out, how can I write this in such a way that it looks like things from my table? So that I can say, okay, I can apply things that are known. So that's actually the bulk of the work. That's why this is actually the square that got really highlighted here, is how can you figure out to take your problem and prepare it for going into the table. Because once you do that, you say, oh, I look it up. And so actually applying the table is very straightforward. And then you have your answer, and then you do a little bit of post-processing. Now, the post-processing just means you clean up your expressions, simplify, maybe solve for a function. So the bulk of the work lies here. What happens before you take your Laplace transform? So that's what I want to spend some time talking about today. And there are sort of three things I want to make sure you're comfortable with. Because I think these are three skills where you'll see them pop up from time to time. And we just want to make sure you're ready. So that's partial fractions, piecewise functions, and remembering how to handle exponential functions. Because sometimes this throws people off, and I just want to make sure it doesn't throw you off. This is not really much of a skill. It just says, hey, don't forget, exponential functions have this really cool property. E to the power a plus b, e to the a times e to the b, and it's the same e to the a minus b, e to the a times e to the minus b. In other words, if you have addition or subtraction upstairs, you can separate it. All right, so that's what I want to talk about. So let's start with partial fractions. Now, why is partial fractions so important? And what is partial fractions about? Well, I have an example that we're going to work through here. But before we work through it, I just want to emphasize, why do we care about partial fractions? Now, partial fractions gets its name from dealing with the expressions that look like polynomial over polynomial. You have to have that. If it's not a polynomial over a polynomial, you can't do partial fractions with it. Okay, so great. But why is it so important to us? And the answer is, if you look at pretty much any inverse Laplace transform problem that we can ask you, and that you have any hope of being able to answer, it always has the following form. Polynomial over polynomial, and maybe something on the side that looks like e to the minus as. So this is all inverse Laplace transform problems look like this. And so once we know how to handle the pre-processing for these things, then we're ready to go. So that's good. So now the question is, how do we handle it? All right. So the place to begin is to remember, where can we do partial fractions? Can I do partial fractions with this entire expression as it's currently written? And why not? No, we can't. Okay, someone said we have to factor the bottom. Yes, that is one issue, but there's something else. The e to the minus 3s, that's not polynomial. Now that's important, because what you will do is we'll think of it as two things. Namely, as the part that looks like a polynomial over polynomial. And that's the part where we do partial fractions. And then we have the other piece, which is the e to the minus 3s. Now, the e to the minus 3s does play a role. And so we'll keep it, but we're going to sort of have it off to the side. And the nice thing is that when you have that e to the minus 3s, when you're thinking about the inverse Laplace transform problems, is that this symbolizes something. It corresponds to a very important thing, and namely, this is telling us how we shift. So whenever you see an exponential function involved, you know your answer will involve a shift at the end. Okay, so we run through it. So let's go ahead and carry this problem through. All right. We'll come back and finish it up. So ignore the e to the minus 3s, because we're going to just pull off just the polynomial over polynomial part. Someone said we have to factor the denominator, and that's true. Does s squared minus 3s plus 2 factor? Yes. What does it factor as? Okay. Now what if it hadn't factored? What would we do? Well, I'm sorry, what? Complete the square. Yeah. So what you should end up with, all your terms downstairs should either look like, your denominators will look like either s minus a, or they'll look like something like s minus a squared plus b squared. So those are the two things that you should expect downstairs. And so if you can't factor that quadratic, that means you can do completing the square. All right. Now what happens? Okay, so equals. And so the key here, and this is, so there's a few key steps. First key step is to make sure you're only grabbing the polynomial over the polynomial. The next key step is making sure you know how to get the form right. And so someone was saying, it's some constant, usually we use a, over a piece, and some other constant over the other piece. All right. Clear out the denominators. How do we do that? Multiply by what? Yeah. Look at the denominator of your original expression. That's what you use to clear things out. S minus 2 times S minus 1. So we end up with 4 times S minus 3 is equal to A times S minus 1 and B times S minus 2. Because what you can think of is just think about, okay, I multiply here, S minus 2, the S minus 2's cancel. So that's why I'm left with an S minus 1. And here the S minus 1's cancel, so I'm left with an S minus 2. Now, at this point, you have to solve for A and B. So what are some ways we can solve for A and B? Sorry, what? Pick an S that makes things cancel out. All right. So we'll call that to make good choices. Yes, Grandma, we will make good choices. And now, how do you make good choices? Well, we like zeros. That's probably something you're going to get out of this math class. Really out of all your math classes. Like, you know what? I really like zero. It's a really wonderful tool. I don't like it in my bank account, but in my math problems, it's fantastic. It's wonderful. Okay, so in this case, what are some good choices? 1 and 2. So if you choose s equals 1, what does the left-hand side become? 1. What does the right-hand side become? And negative b, because the first term drops out. Okay, so b equals negative 1. If s equals 2, 8 minus 3 is 5, equals a, or, and the b drops out, or we could just say a equals 5. Now, suppose you can't make good choices for some reason. Or maybe you just don't have enough good choices to make. What's another thing you can do? What? System of equations coming from what? Yeah. So this is expand and collect coefficients. I have no idea why I'm switching between uppercase and lowercase. I don't know. But the moral is, think of it as a polynomial. And so you expand and group. You have coefficient in front of s, coefficient in front of b, and then that gives you a system of equations to solve. And if there's anything that we've gotten pretty good at in this class, it's solving system of equations. We're really good at that. So we'll skip doing that here. Okay, so now we've done our partial fractions decomposition. Let's continue with our problem. So we've gone to this piece is a over s minus 2 and b over s minus 1. This is a place where it's very easy to make a copy error. So go ahead and slow down a little bit and just make sure you have the right number going in the right place. So it's like, okay, I see a is 5, so it's 5 over s minus 2. And it'll probably be good to put it in the front. So 5 times 1 over s minus 2. And then b is negative 1. So the b goes with the s minus 1. So that would become minus 1 over s minus 1. And don't forget your e to the minus 3s term. Okay. Now we're ready to do a little bit of saying, well, what happens to our pieces? Okay, so 1 over s minus 2, what would this normally go to? E to the 2t. 1 over s minus 1, what would that go to? E to the t. See, you probably know the table so well, it's like, I know that. I don't even have to think. And the e to the minus 3s is a shift. So when we see that, we think shift. Shift by how much? Shift by 3. E to the minus as, shift by a. So now we're ready to do our inverse Laplace. And this will go to, well, we'll have our, everything's being shifted by 3. So 5, and it won't be e to the 2t, it'll be e to the 2 times what? T minus 3. So what we're going to do is, because we're shifting by 3, we're going to replace these pieces where we have t going to t minus 3. Minus e to the what? T minus 3. You can even put parentheses in there if you like. Parentheses are good. Parentheses save points. Anything else? Yeah, we have that. Someone was calling it earlier, our fancy U. See that little like swirl? Wow, fancy. Don't forget that. T minus 3. Well, we're going to always judge you based upon how nice your U looks. If there's not enough of a curl, we might have to dock you a small point. On the other hand, if you have too many curls, that's also just as bad. So the key is just like once around. Sorry, what?
Each curl is the point effect.
You think? Wow. I can see somebody just. Okay, there's 100. All right. So that's the idea. Now, so like I said, all inverse Laplace transform problems take this form. And so that's why you should expect. In fact, we know it's going to be there. We know there's going to be an inverse Laplace transform problem. So you have to be ready to handle that. But once you have the procedure down, you're good to go.
What do you set this equal to at the end? If the box didn't agree, what is it equal to?
Well, I mean, normally, so the question is, what would this be equal to? Normally, what you would start off with is saying, well, this is our capital F of S, and then this part here would be our little f of t. That's what we would normally think of. But usually they'll phrase the problem as, find the inverse Laplace transform of this, and we say, okay, the answer is that. So, while we're here, let's just do one quick reminder. So we'll just make up stuff for the numerator. We're not actually going to go through and run through the whole problem. Suppose I had s plus 1 squared times s squared plus 1 downstairs. What's on the other side? A over what? S plus 1? B over s plus 1 squared. Good. That's right. So A over s plus 1, B over s plus 1 squared, and CS plus D over s squared plus 1. Now, sometimes this throws people off and like, really? And the answer is, yeah, that's right. That's right. This is the right thing. So the thing here, now let's talk about the s squared plus 1. See, s squared plus 1, you can't factor it further without getting complex numbers. So we call that irreducible. It's an irreducible quadratic. And so if you can't go any further and you have a quadratic down here, that's why you have to have a term with an s on it upstairs. So if you can't factor the denominator further, you have to have that cs plus d. And I say, well, wait a second. Here, you have an s squared. Well, yeah, but look at what it's really, the s plus 1 is what you q off of. And s plus 1 would be first order or linear. So that's why we only need a single number upstairs. So make sure you know how to get your decomposition. And if we were to clear the denominators, what would I multiply by? I know not many people make this mistake, but I just want to make sure nobody makes this mistake. What do you multiply by to clear the denominator? Yeah, Q, you use the original expression. So some people make a mistake and say, oh, I'll multiply by this, and by that, and by that. Well, what happens if you multiply by s plus 1 and plus s plus 1 squared? You're really multiplying by s plus 1 cubed. You went too far. You went too far. So go just the right amount. That's what we want. Okay, so that's what I want to say about partial fractions. Okay, let's talk about piecewise functions. There's not too much going on. It's pretty straightforward. And we'll just do an example. So we'll have to make up a piecewise function. How do you wish your function to start? Let's make it mildly interesting, but just mildly. Our tangent, not mildly interesting. Our tangent is incredibly interesting. That's like, that just wakes you up in the morning like, whoa, it's an arctangent kind of day. Sorry, what? Sorry, my hearing is not very good. 99t? No, that sounds like the start of a song. 99t inside the cosine, 99t inside. We take one down, we pass it around, end up with t squared plus sine t. All right. Well, how about pi t? All right. T squared plus sine pi t if t is less than 1. And something else if t is bigger than 1. You don't want to. Yeah, okay. How about e to the t plus 4t? All right. You're trying to make it hard. You don't want it to be hard. You want it to be easy. You want us to actually finish the problem. Okay. So how do we handle these functions? Now, it may be given to you in this format. It may be given to you in a slightly different format, but you have a piecewise function. The key here is you identify where you change. Where do we change? Yeah, and it's pretty easy to figure out where do you change. You just say, well, look at your bounds. It's like, well, I have one behavior below one behavior after one. So the first thing we do, and remember, we're in our preprocessing mindset. So preprocessing mindset says, I am working towards making this look like something on my table. And so we say, okay, what are things on our table? And so whenever you're dealing with piecewise function, the piece on the table that you cue off of is this formula right here. That f of t minus a, u of t minus a, and that becomes e to the minus as f of s. That's where you cue off of. And so that's what we're going to be doing. So we use this unit step function. That's our on-off switch. So we want to make sure we're comfortable using that. So we say, okay, so we rewrite our function. So we say, okay, f of t equals, and then what you have is you have your initial part. You say, okay, what's happening initially? Plus u t minus, and this is where we switch. And then you have, we turn off something, and we turn on something. So this is the form. What's our initial part? Yeah. It's what's happening at 0. So t squared plus sine pi t. Okay, where do we switch? We switch at 1. Okay, so that's t minus 1. What do we turn off? Yeah, the part initially, t squared plus sine pi t. And because we turn it off, we subtract that. So these will cancel. And what do we turn on? Well, that's being added. E to the t plus 4t. All right, great. Now, are we ready to use our table? Or is our processing done? No. What's wrong? Well, if we zoom in, there's this part right here. Do you see how it says f of t minus a? So that's the work. So this initial part, we're fine with it. There's no problems here. But the problem, and the thing that's going to make us go, ugh, for a few minutes, this part needs to look like t minus 1. And right now it doesn't. So how do we fix that? Do you know? Someone is very excited.
Manipulate all the t terms, so that's t minus 1.
Wait, what?
It's manipulate t terms, so that's t minus 1.
Okay, yeah, so manipulation, another word for rewrite. Rewrite the t terms so they look like t minus 1. So how do you rewrite the t terms so they look like t minus 1?
We have to add something, and we're going to have to subtract something.
You're being very mysterious. What do I have to add and subtract?
On the table, we can do convolution of t plus 1. Well, ft.
You want to do convolution? What? What?
There's a table that minus f.
Aha. Someone has suggested, hey, cool fact, t is t minus 1 plus 1. It's totally true. Totally true. And so this is the key. So this is how you do your rewriting. And what you do is you're going to go through, and everywhere where you see a t, and this is where it gets, I don't want to say painful, but painful. So instead of t squared, well, it's t minus 1 plus 1 squared. sine of pi t minus 1 plus 1. Okay, and there we go, plus e to the t minus 1 plus 1 plus 4 times t minus 1 plus 1. Okay, there you go. And you're probably thinking, that does not look better. It does not. But it's not about looking better visually. It's about making it compatible with the table. So if we go a little bit further, what happens? Well, t minus 1 plus 1 quantity squared would do what? It would become t minus 1 squared plus 2 times t minus 1 plus 1. So in other words, you can square it out. The sine of pi times t minus 1 plus 1. Now this pi can distribute to the 1. If I have a sine function and I add pi on the inside, what does that do to the sine function? Think about the unit circle. If I'm on the unit circle and I go pi away, where am I at? Well, you're exactly opposite, right? Yes? No? Yes, it's true. True story, true story. You know, if I think unit circle, if I'm here and I go pi is halfway around. So I'm directly opposite. So that says the plus pi here, I can pull out and becomes a minus sign. Pi t minus 1. Okay, so that's the first part. And, well, there's a minus here, so minus minus makes that a plus. Sorry, you have to keep track of all the signs. E to the t minus 1 plus 1. What's another way to write that? It's the same as e to the t minus 1 times e to the 1. And this last part, well, that's 4 times t minus 1 plus 4. And you can squeeze a little bit more together, because why not?
Wouldn't the sign term still be negative?
There's a minus here.
Yeah.
So there's a minus coming in, and then there's another minus coming in. So two wrongs make a right.
Oh, okay, you distributed.
Yes. So you have minus t minus 1 squared. There's a minus 2 times t minus 1, a plus 4t minus 1, which makes a net of plus 2 times t minus 1. You have a minus 1 and a plus 4, which makes 3. You have a sine pi t minus 1. And then you have an e times e to the t minus 1. Now, are we ready for the table here? Yes, yes. See, there's the pre-processing part. The pre-processing part's the hard part. But once you're done with the pre-processing, this u of t minus 1 would translate to e to the minus s. Now, this t minus 1 squared, well, you treat it like t squared. Do you know what t squared goes to? Two over s cubed. T minus 1 you treat like t. What does that go to? 1 over s squared. Good. 3 goes to 1 over s. Sine pi t. Ooh, that's a fun one. You know what that one goes to? Now, of course, you have your table. So you can just say, table. Like, okay, here's the table. Does anybody know it? There's a pi upstairs and downstairs. S squared plus pi squared. Now this e, what does that go to? It's just e, it's a constant. E to the t minus 1, because we're in the shift, we treat it like e to the t. E to the t goes to 1 over s minus 1. And there we go. Now that's actually just part of it. You still have this other part in front. Well, but that's more straightforward. It's 1 over s cubed plus pi over s squared plus pi squared. Because those are straightforward functions. So there's the Laplace transform of our function. See? Easy, easy. Well, maybe not easy, but possible. There we go. Possible. It's possible. Be comfortable with working with e to the a minus b. So for instance, if you saw e to the 2 minus s over s minus 2, this won't be very profound, but I just want to make sure you'll do it. 2 minus s in the exponent is not really compatible with the table. Because whenever we have things in the exponent in our table, it's like e to the minus something s. There's no constant there. So what do? Yeah, so it's e squared e to the minus s over s minus 2. So you think of it as the e squared as a constant pulled out to the front. Or if you like, this is e squared 1 over s minus 2 e to the minus s. Now, 1 over s minus 2 would normally be associated with what function? E to the 2t. E to the minus s is telling us to do what? Shift by 1. So, if we put this all together, this will go to, we have the e squared, then we have e to the 2, but it's not e to the 2t, it's e to the 2 times t minus 1. And then, what else? U t minus 1. Can we clean that up any further? So it's e squared e to the 2t minus 2. And then what? E to the 2t, because you can add the exponents. So be ready. You can simplify expressions. You know, recognize you can break things apart. Recognize you can put things back together. But it's important to be able to break things apart. Last thing I want to talk about. So we talked about partial fractions. That's what often will show up when we talk about doing the inverse Laplace. You just have to be ready. Piecewise can show up when you're doing, say, take the Laplace transform of this particular function. This just shows up as something we want to handle. The reason I wanted to talk about convolution is it does show up on our table, but it only shows up by saying, hey, there's this thing called f star g, but it doesn't say what f star g is. So I want to make sure you know what f star g is. Do you know it? So f star g, it's a way of combining two functions together. It's the integral from 0 to t, f of tau, g of t minus tau, d tau. And that's the definition. Now the reason we like this is that we have this idea that f star g, if we take the Laplace transform of that, it's the same as the Laplace transform of f times the Laplace transform of g. So in other words, it's super easy to take the Laplace transform when there's a convolution involved. Now, in the other class I taught today, they said, give us an example. Can we see an example? Oh, okay. Sure. So we made one up. Do you want to see an example? Yes. All right. So we're going to make one up. So your job is to pick some functions. Not the rules, some functions here. We need you to pick two functions. Cosine of what?
5t.
Cosine of 5t is our first function that has been picked. Star. We need a second function. Cosh. All right, we can do cosh. Keeping it. Cosh just adds an h. Do you still want 5, or we can make another number? 2t. Okay, so now you might say, where's the problem, Steve? Let's suppose, let's just make the question this. Integral 0 to t, so I'm applying the rule. Cosine of 5 tau, and then I have cosh of 2 times t minus tau, and I say d tau. And now, here's my question. So the question, find the Laplace transform of that. Now, suppose you just had that question. So you just saw this, you're walking down the street, and someone said, hey, can you tell me what the Laplace transform of the integral from 0 to t cosine 5 tau cosh 2 times t minus tau d tau is? You're like, what? What? But how do we solve this? What do? Yeah, we recognize that it is a convolution, and they say, oh, it's a convolution, and in particular, it's these two functions that we've convoluted together. Now, what does cosine map to? Well, there's a rule. So cosine 5t would map to s over s squared plus 25. So I'm reading the rule. Someone once said, you should never mix s's and 5's together. Yeah, I agree. My s's and 5's do look suspiciously alike, but that's an s on top. Cosh also is on here. So cosh would map to s over s squared minus a squared, so s squared minus 4. So, given what you know, what's the answer to this question? It's these two multiplied together. So the Laplace transform of this, our answer is 5, whoops, even after I said 5's and s's shouldn't be mixed together, s squared over s squared plus 25, s squared minus 4.
Would you ask us to do the inverse Laplace transform or something like that then on the example?
Now, if you do the inverse Laplace transform of this, what's the way you would normally do this? You'd partial fraction it. Yeah. And so actually what you can do, this is one thing you can do. So if you ran partial fractions, you'd end up with something over s squared plus 25, something over s minus 2, something over s plus 2. And you'd take the inverse Laplace transform. And what you'd end up with is you say, oh, I can actually do this integral by doing the Laplace transform, doing partial fractions, and undoing it. So that's another application of convolution.